So in the last class, we started taking a deeper dive into the state graphs and state tables. We basically just finished the state graph example, didn't get to the table, and we'll get there today. The example that we took was a sequence detector, and we were looking for a specific sequence 101. Whenever you get this 101 sequence, you are creating a 1 output, and otherwise the output was always 0, right? And we started with this description of the system. Instead of showing the timing diagram, we showed a tabular format. And then we started drawing a state graph. So basically, we started describing every situation and started treating it like a state. And the state could be S0, S1, S2, or however many states you need, depending on the complexity of the system. And let me fast forward to this one. And without repeating the discussion that we had here, this is the new slide that we'll start from today in today's class, right? So let me repeat this graph one more time so that you are all on the same page, and then show you how to convert that to a state table. Okay, so remember, we are looking for 101 as a sequence. Okay, our system always starts with 0 because there was nothing before we started. So it's 0. S0 is the state where we start. So it's kind of like the reset state. Every time you have to reset, you go back to S0. Okay, so now if you get another 0 while staying at S0, you should stay at S0 because that is the state with absolutely 0. So as long as you keep getting 0, you stay within this state. That's why you repeat back the same state, and your output is also 0. So remember this notation. The first number represents the input that you get, and the second number after the oblique shows the output that you provide. Okay, this is the way we represent a specific. In today's lecture, you'll see a different type of representation soon, right? Not every state graph will be like this. This is a special type of state graph, and I'm going to explain what type of a state graph it is after we are done with this discussion. But for the time being, take it for granted that this is how you represent input and output. All right. Next, what if you get a 1 while you are at this research stage? So maybe you are getting 0, 0, 0. Suddenly you get a 1. And you suddenly become interested. Hey, okay, something interesting going on here. So we need to remember that we have had a 1. But S0 will not let you remember that because S0 is meant to show 0 all the time. So what you do is you get to a new state that remembers that, hey, I just have 1, 0 so far. So when you get input 1, you get to a second state, but your output is still 0 because you haven't received the magic word yet, right? Okay, so you are at a new state. Okay, now notice, while here, so your state was, say, 1. If you get another 1, will that be more exciting? Will you feel like, hey, we are closer to the magic word or not? Tell me. Are you closer to the magic word? Are you any far out from the magic word, folks? No, because if you keep getting 1s, you are essentially getting ready for the next one, next 0. Until you get the next 0, you are still in the same state. S1, S1, S1. So as long as you keep getting 1, you stay here and stay prepared for the next 0. Are you good so far? Okay. So the moment you get another 0 here, all of a sudden you are getting interested because 101 is your magic word. So you're one step closer to the magic word. So it's different. So you need a new state to represent that. And the new state is S2. And you go from S1 to S2 when you get a 0 after the first one, and your output is still 0 because you haven't received the magic word yet. So your output is still 0. Finally, at this stage, see, it can be really detrimental if you get a 0 at this stage. If you get a 0, all of a sudden, your hopes of getting the magic word is gone, right? 100, no. It's kind of like, okay, no, it's not even close. We will start from ground 0 again. So basically, you have gone back to the first state, S0. So you're close to getting the magic word, but all of a sudden, you got a 0, and then you go back all the way. Does that make sense, folks? Okay. But what if instead of 0, you had a 1? That means you have the magic word now. So you had 1, 0, and 1. If you get a 1, notice, interesting part is your output is now 1. This is the only case where your output is 1 when you get an input 1 here. But which state do you go to? After you get the magic word, let me clear it up again. So imagine you have 0, 0, 1, 1, 1, 1, 0, 1. So you have the magic combination here. But the next stage will only see this one. It will only see this one, right? So it is getting ready for another 0 and another 1. Are you still with me? So after you create this magic word and show an output 1, you will go back to this second stage because that had just 1, 1. And then if you get another 0, you get to the next level, you get another 1, you trigger again, and so on. Does that make sense? Okay. I don't know if you got a chance to try it out at home. If you did, I hope it makes sense. If you didn't, I highly recommend. I couldn't stress this more enough. And I know, like, I'm trying to give you a homework where you have some practice on this. Okay. So hopefully that will help bolster some ideas. Okay. So are you all good so far with the revision? So once you have this state graph, there is another way to present this in a tabular format. This is called a state table. So state graph to state table. Here is how we get to a state table. Imagine, first of all, how many states did you need? 3, S0, S1, S2. Excuse me. So every flip-flop can store 1 bit of information. Okay. If you have 1 flip-flop, it could represent 2 states. Remember, with 0, you could represent S0. With 1, you could represent S1. But who represents S2? That means a single flip-flop cannot represent 3 states. So you need another flip-flop. So with 2 flip-flops, you can represent actually 4 states. 0, 0, meaning both flip-flops have 0. 0, 1, meaning one has 0, other has 1. 1, 0, flipped, and 1, 1, right? So both has 1. So these combinations could represent 4 physical states. But we need 3, but still you have to use 2 flip-flops anyways. So I am going to, first, before I go move to that state representation, I'm going to tabulate this graph. Hear me out. So these are my 3 states, S0, S1, and S2. Please help me go through the graph and put it on the table together, because only then it will be easier to understand. Okay. So when I'm at S0, this is my present state. I'm trying to get to the next state. And what happens to the next state depends on the input, whether the input is 0 or the input is 1. So we will see what happens when the input is 0. So I'm at S0 here, and my input is 0. What happens there, folks? Just look at the graph and tell me what happens. What is your next state? Is 0. Your next state is still x0. Okay, by the way, but if you get a 1 as input, what happens to the next state? Next state is S1. So your next state is S1. Can you read it from the graph and put it on the chart? Okay, let's do it for one more example. S1. So you are in S1. This is your present state. When you get a 0, do you stay here or do you get to a new state? New state, which is S2. So when you get 0, you get to S2. But when you get 1, you stay at S1. Are you good? Finally, S3, S2. Imagine we are at S2. And when you get a 0, you get to S0. See that? But when you get a 1, you go back to S1. So essentially, it is nothing new. It is whatever is being presented in the state graph, but in a tabular format. Okay. Finally, there is one more column left, which we need to talk about. That is the output. And this is easy enough to just, extract from the graph. So when you are at S0, notice, when you are at S0 and your input is 0 again, what is your output, folks? Tell me. Can you see I'm marking on top of it? You see that? Your output is 0. Just plug it in. When you are at S0, but your input is 1, what is your output? 0 again. Sorry. 0 again. Are you good? So most of these will be 0, except for the case where, let's see, S2. Say you are at S2, and your input is 0. This is your input. What happens to the output, folks? 0. But when you are at S2, your input is 1. What happens to the output? 1. So you see that? You can easily look at the state graph and convert this to a state table. You might be wondering why. Just hold on. We'll see why why this table is. Yes.
Always 1, 0, 1, or can it be anything that you provide?
Yeah, it could be anything that you choose before you design the system, by the way. So the 101 is a random choice, basically, without any loss of generality. You can try to redesign the same system with, say, 111 or 011 or something, and things will change. Things will look different. But there is nothing special about 101. But the problem is, once you decide on a code, you are designing the entire system for that particular code. So your overall hardware design will change. Okay? If you want to dynamically change the input, that becomes more complicated. That is possible, of course. But at this point, we are just learning how to design these sequential circuits. You are not trying to add features yet. But it would be nice. This is called dynamic tuning, meaning you design a circuit, but you can take some input from the user. Hey, my key should be now 101. Change. My key should be now 111. Change your hardware. And oftentimes these hardware changes are done through multiplexers. Okay. So, but we are not going to get to that degree of complexity. For now, whatever you design, you stay with it. If you design for 101 as a magic word, it will always be there. If you change your code, you have to change your hardware. Okay, because you'll see hardware is closely linked with the code that you have chosen. Are you all good so far, folks? All right. So we are at the state table. We are moving from the state table to a transition table. And if you pay attention, it will be like super simple. Ready? Are you ready to pay attention? Okay. Is this table new? Or did we just see it in the last slide? Exactly the same. So I copied it over here. What I'm going to show you is this is an easier representation for us to keep in mind. State 0, state 1, state 2. But the binary systems don't recognize S, A, B, C, like nothing. It only recognizes zeros and ones, right? As you know. So I'm going to represent specific states with specific binary combination. So I just told you that with 2 flip-flops, you can have 4 states, 0, 0, 0, 1, 1, 0, 1, 1. Okay? But you just need 3. I'm going to choose specific binary combination to represent a specific state. So without any loss of generality, I'm choosing S0 as 0, 0, S1 as 0, 1, and S2 as 1, 0. Like in series, basically. 0, 0, 0, 1, 1, 0. Any problem? So 1, 1 is essentially unused because I don't need a 4th state here. Are we good? So once you do it, can you do me a favor and replace S0 with 0, 0, S1 with 0, 1, and S2 with 1, 1, 0? Can you help me do it? If you do it, if you replace all of this, you end up with this table. Right? Essentially the same thing, except for the fact that you are representing S0 as 0, 0, S1 as 0, 1, S2 as 1, 0. All right? Is it clear so far for everybody? Okay, now we are also, instead of, using this verbal representation, next state, present state, I'm going to make it more formal. It's kind of like relevant to Boolean algebra. So present state needs 2 bits, as you see. So I need 2 flip-flop, maybe flip-flop A and flip-flop B. The output of flip-flop A is A. The output of flip-flop B is B. So 0, 0 represents the output of flip-flop A and B being both 0. Make sense? Okay. So this is so one given state of the system is represented by the states of 2 flip-flop, A, B. If A is 0, B is 0, you have a given state. If A is 1, B is 0, you have a different state, and so on. So this is my present state, AB. That's the other thing that changed. Instead of calling it present state, we're going to show it as AB, because you have 2 flip-flop outputs, A and B, and together they create the state. Now, can anybody tell me, do you remember if the flip-flop output is Q, what is the next state output represented as? You should remember Q and Q plus. Remember, that's how we used to do it. Similarly, if A is the next present state, what will be the next state in your mind? A plus, just to show that it is the next state. Okay, so our next state will be A plus B plus. Are you good so far? Why do you need, again, just to reiterate, why do you need two flip-flops? Because you have three states. One flip-flop can only represent two states. To get to the third, you need two flip-flops. To get to the fourth, you still need two flip-flops, by the way. If I give you 5 states, how many flip-flops will you need? Tell me. 5 states. 3. But many of the states will be unused because you can have 8 states, but you just have 5. So up to 8 states, you'll need 3 flip-flops. But then if I give you 9 states, you need 4 flip-flops. This is the nature of binary, as you can see. Okay? So are you good so far? Can you see the change between the conventional state table versus a transition table? So you change the state table to a table that is basically more close to Boolean algebra. Okay? And the output is mentioned as Z. So these are same tables, but representations are different. So once you have this table, can you take a look at it and see? This is the exact same transition table that we saw in the last slide. Okay, this is the same transition table. But then what you do with the transition table, that's where the magic comes. So through all these steps, I'm trying to make a formal approach towards designing the sequential circuit rather than just observation-based approaches, which we tried in the last class. Okay, we tried using some observation, and I told you that there will be a formal approach that you will learn together, and we are doing it today. Basically, you started with a graph, you converted to a state table, then you converted that state table to a transition table. We are at the transition table now. We're going to convert this transition table into what's called the next state map. Next state map. Okay. Super simple. Let me show you. It is essentially a K-map. Sounds different, but it is not. It is the same thing. It is a K-map. And I hope if you remember K-maps, it will be easier for you to understand this. All right? Let's do it together. I will start with, just imagine how many things will I need to keep track of? I need to keep track of output for sure. But also, this is the tricky part about the sequential logic versus combinational logic. Combinational logics had input and output. No present input and next input. Like, you see my point there, right? Okay. But for sequential logic, A and B can be treated as inputs. But A plus is your output. You see my point here? Although A plus and A are coming out of the same terminals, but they are not the same because they are in different timestamps. Okay? So how can I decide on an expression for A plus? I will treat A plus like an output. That is my next step, my next state, basically. And that will depend on A and B as well as X. Are you still with me? Okay. And how about B plus? That is also going to depend on A and B as well as X. So there are 3 things that will determine A plus and B plus, and of course Z. Z is for sure going to be determined by what happens to A and B. Okay, let's see. So notice this is a K-map. In the K-map, we show all the variables. Notice our variables are A, B, and X. A, B, and X. Okay? So if your AB is 0, 0, 0, 1, 1, 0, 1, 1, do you see why we have 1, 1 here? This is basically K-map. You need to design it in a way that only 1 bit changes. So although you don't have 1, 1 here, you still insert 1, 1. And we're getting that in a second. Even if you don't need it, you will have to insert it in the K-map. Otherwise, K-map will not work. And then for X, you have 2 options, 0 and 1. Excuse me. Is that new? No? Okay. So I'm going to focus on A plus, looking at A plus. Okay. Notice when A, please work with me together. That way, you'll not be confused and it will be super easy. Trust me. Ready? So I'm looking at AB 0, 0 and X equals 0. Where is that combination in the table? AB 0, 0 and x equals 0. Did I find the combination? Okay. But what am I looking at? Am I looking at a plus, b plus, or just a plus? I'm looking for just a plus. What is a plus? 0. So I can plug in 0 here. Are you good? We'll come back to b plus later, but let's just take a plus for this one, for this K-map. Okay. Let me take a random example here from say 1 0. Let me change the color. Okay. 1 0 and 1. Okay. So where is AB10? This is AB10. And where is X1? This is X1. So this is the combination I should look at. You see? But do I need both A plus and B plus? I need just A plus. What is A plus here? 0. So I'm going to plug in 0. Are you good? Okay. One final example. Let's take this one, 0, 1 and 0. Where is 0, 1? This is 0, 1. And where is X0? This is X0. For that, I should look at this combination, but only at A plus. What is the number corresponding to A plus? 1. So you plug in 1 here. So essentially, you can just read from this transition table and create your K-map. Is that clear? Is that clear? It will be really clear after you try it once from scratch. Don't look at the slide. Start from the transition table, try to make the K-map yourself, and then see whether it matched. And then you'll have the, oh, I see. Otherwise, it'll like, oh, he said that. Right? All right. So one interesting point, there was no 1, 1 required in this particular example. So do you care about the output for 1, 1? No. So no matter what happens to the input, 0 or 1, we don't care. So that's why you have this D, don't care. See, another example of how you can use don't cares, because you simply don't have that state. That state will never appear. Okay. All right. I will get to what you do with the K-map later on. But can you make the K-map, folks, from scratch now? Okay. Can you repeat the same process for B plus? So this was for A plus. Can you do it for B plus? So wherever we were looking for A plus, you see the next digit instead, B plus. So I can have a separate K-map for B plus. Similarly, okay, I will show you what happens to Z. I'm going to do the K-mapping for Z now. This is Z, K-map for Z. Ready? One last time. Let's do it together. So let's take this random example, 0, 1 and 1. Where is AB01? Here it is. And where is X equals 1? Oh, no, not this column. I need the Z, right? X equals 1. So by the way, for 0, 1 and 1, what do you have? Z equals 0. So you put Z equals 0. Exactly the same approach. Nothing changes. Okay, let's take this one, 1, 0 and 1. This is my 1, 0. This is 1. For this combination, your Z is 1. So you just put 1 here. And can you do it for everything else? By observation? Okay, so you can populate these 3 K-maps. Once you do so, after you have a K-map, I don't have to tell you how to get the function out of the K-map, do I? Let's do it quickly one more time. So let's start with this one. I mean, it is already shown that you can group these two. You can treat this don't care as a 1, right? It is like whatever helps you. If you treat it as 1 and that helps you create a bigger group, treat it as a 1. Do I need to do anything with this other D? I don't need to cover it. So I will just ignore it. I will treat it like a 0. We have covered it before, so I'm not going to discuss this in that degree of detail. So this is our grouping. And what doesn't change here in this column? X. What is the value of X? 0. So I should have X prime. And between these two, what is not changing, folks? A or B? B doesn't change, and B is 1. So you have X prime B. So your A plus is X prime B. You see that? You have had enough practice with K-map, so I'm assuming you are okay with it. All right. So next, here, you have another bigger group, and your don't care is actually helping you create that group. Otherwise, you'll not have that, 4 element groups, right? You see my point? So what is not changing here? X is not changing. So you have X, but Everything else is changing, by the way. So just X, that's it. So B plus is just X. Are you good? Finally, for Z, you have another grouping. Let me clear it up and then come here. This is your grouping for Z, and what is not changing? X is not changing, and here A is not changing. So can I say it is AX or XX? Yes. Yeah, of course. Yeah. So let me show you again. So I didn't get Z from AB plus. I got everything is coming from AB. Okay. AB and X are your inputs. So notice this is AB and this is Z. Okay. Which we, if you remember, we plugged in these values from state graph. We decided on the state graph what's going to be my output. Should my output be 0? Should it be 1? By describing the overall strategy, right? It is more like a flow chart, for example. And then you created this table. Once you have this table, now when you go to the K-map, let's take 0, 0, AB 0, 0, and X equals 1. So AB 0, 0, X equal 1. What is the value of Z? 0. So you just plug in 0 here. Okay. So let's get to the next one. Your AB is 0, 0, X is 1. So AB 0, 0, X is 1. What is the value of Z again? 0. Right? So you keep repeating this for every combination and go back to the chart and plug in the values. Except for the fact that 1, 1 doesn't even exist in the table. So for 1, 1, you don't care. So you have these don't care conditions. Is that clear now? Any other questions? Okay. So I assume that we can get from this transition table to the K-map safely. And you can convert these K-map expressions into functional representations. Are you good so far? Okay, now what? This is the last step. This is the last step. So you basically do this next step map to a circuit. You convert this next step map to a circuit. Once you get these K-map expressions, it is now easy for us to make a circuit. First, you have to pay attention to this transition first, okay? I told you we need 2 flip-flops. But did I tell you that do you need an SR flip-flop? Do you need a D flip-flop? Do you need a T flip-flop? I didn't tell you that, did I? Remember in one of the previous examples for parity checker, we used a T flip-flop, right? We decided to use a T flip-flop. But now for this example, we're gonna use a D flip-flop, all right? And by the way, D flip-flop is the most common because you can always convert it to other types of flip-flops. But anyways, D flip-flop. What does D flip-flop do? Notice, it takes the data and it sends to the output. If you can choose the input accordingly, your output, hear me out again, next state output will be your input. Do you agree with that? Whatever you provide as an input, your next state output will be that. Your next state, not this state, the next state. So what are these expressions, folks? A plus, B plus is the next state output. And I want the next state output to be like X prime B and X. You see that? So what I'm going to do is I will provide this as inputs to the D flip-flop. And the D flip-flop during the clock edge will create the next state output. Are you good? Okay, let's see. So that's why first, it is super simple. A plus is X prime B. Take X. This is your X input. This is your X prime because you have an inverter. And this is your B. B is coming from the output of the flip-flop. So the output of first flip-flop is A, output of the second flip-flop is B, and you take X prime and B, and this is an AND gate as you see here. What do you get here? You get X prime B, which is A plus. You remember that? A plus is X prime B. Okay, so this is essentially you are providing A plus as the input of this D flip-flop so that when the clock comes, it will be A plus here. A to A plus. Does that make sense to everybody? Okay. What else? How about B plus? B plus is just X. Notice, this is your X. You take it, you just provide it as this to the input of the next flip-flop. And at the next clock edge, this will be B plus. B plus is just X. Make sense, folks? So, and then finally, what happens to your other output, Z output? Z is X and A. Notice X and A. So you take X and you take A. This is where A comes from. And that's what gives you Z. Do you see that? It is a closely coupled combinational logic and sequential logic to achieve something, to achieve an application per se. The application is to detect a specific sequence. Everybody okay with it so far? And by the way, if you change 101 to be the magic combination and change it to say 111, this combinational circuits will change, by the way. You still have two flip-flops, but this combinational circuit connections will change. Okay? Does that make sense? All right. Now, any question? I'm not trying to rush through here. If you have any questions, don't hesitate. Okay. So what I did was I tried to represent these three equations together represents the overall system. Not just Z, not just A plus, not just B plus. If you are getting confused about A plus and A, remember, whatever is A plus for this time period will be A for the next time period. Whatever is future today will be present tomorrow. You see my point here? See my point here? So notice we are sending A plus to A because A plus will actually become A for the next clock edge. And then you have a new A plus, and then you have a new A plus, then you have a new A plus. So essentially, when I say Z equals XA, it is taking the current state as input. And the next, yes. Which one? Sorry. Yes, base orientation is for 1-1. Yes. Yeah. That first of all, yeah, that's a great question. You may not be able to. It is not as simple because your state graph. Did you get the question? So, first of all, we were looking for a sequence of 1, 0, 1, and that's why we ended up with 3 states because you had to remember every one of them 1, 2, 3. But then you have other things. You have other digits. You need a 4th stage and 5th stage to remember that. So your number of flip-flop will also be more. So this, you cannot just simply cascade this to get it, you see? So that's a great question. So you see my point here. Everything starts from the state graph. And the state graph determines your table. Table determines your K-map. K-map determines your circuit. So that's the strategy. Okay, so now that we have a circuit, let's take a step back. And I kind of hinted at it in the last class. Moore machine and Mealy machine, right? A Mealy machine is something whose output is dependent on the flip-flop output as well as the original input. So notice, this is your final output, right? It is determined by X, which is the actual input. And also, it is determined by one of the flip-flop outputs. The interesting part is your original input X is not clocked. It is not linked with clock. It is not synchronized. But your flip-flop output A is clocked. So you're basically mixing two types of inputs. One that is not clocked, the other one that is clocked. So this type of machines where the final output depends on both original input and flip-flop output is called a Mealy machine. You see my point here? By the way, if you don't, first of all, if you see why we are distinguishing between the flip-flop output and the original input, it's because one of them is clocked, the other one is not clocked. The way I try to put it is one of the inputs is synchronized, meaning it cannot just appear any random time. You know where it is going to come by controlling the clock. But the other input is always available. This X is always available. It is not waiting for the clock. So there are two completely different types of inputs determining your output. One that is always available, other one that is clocked. So this type of machine has a more complex relationship. It's called a Mealy machine. And a Moore machine will do something else. It will not take the original input directly to determine the output. And we'll see an example for that in this slide. So for the same problem, and we can speed it up a little bit here if you pay attention, because it's probably going to be a repeat of many of the discussions we have had. Okay, ready to pay attention? Full attention. You don't need to take any notes if you listen to me properly, because everything is being recorded anyways, and also everything is being shared. So please pay. That is the most important thing, and that is often missing. To try to understand now. Number one. So we're looking for a different strategy to define the same system. We are still looking for 101 to show you the difference between the two approaches. Okay. So here, the way we define this system is you show the output with every state. So this is your state and your output is right here. This is your state, your output is right here. As opposed to, remember in the previous approach towards designing graph, our output was showed as an oblique with the input. Remember, here you only show the input between transitions and you show the output within the state. And you'll see how that changes the game eventually. Okay, so I'm looking for 101. I start with S0. My output is still 0 because I haven't received any 101 yet. So my output is still 0. If I keep getting zeros, I'll stay here. See my point here? Okay, but if I get a 1, this is an interesting situation. I move to a new state, but my output is still 0. Don't you think? Because I haven't received the magic combination yet. Okay, now at this stage, if I get a 0 again, let's first go through the magic combination and let's see what happens when the other things appear. So you get a 1, you get to the next state. You get a 0, you get to the next state. You get a 1, you get to the final state. Are you okay with it? So you get 1, 0, 1, and then finally you trigger. You have a 1 as an output, and others have 0 output. You see what changed? There is a subtle but really significant change here. That is, you have more states. You have one more state now. See my point? I'm not reusing the state. I am creating a new state. So you get 1, you get to the next state. You get 0, you get to another state. You get final 1, you get to another state. Okay? Do you see the strategy here? You first create the winning combination, the magic combination, and then we see the other options. Okay, at every stage, okay, let me show you. Okay, at every stage, imagine here at this point, you needed a 0, but what if you get a 1? If you get a 1, you stay within the same state, don't you think? This is exactly same as what we discussed before. As S2, you were looking for a 1, but if you get a 0, what happens? Remember, anybody? You go back to the reset stage, and that's what you have to do. You go back to the reset stage. That's what you do here. Okay? Okay, finally, when you are at S3, if you get a 0, you go back to this state. If you get a 1, you go back to the second state. And basically, that's the complete graph. The strategy is a little bit different. You start with the winning combination. You first draw the entire state diagram with the winning combination. And you then crisscross all the other connections, considering what happens when you don't get the winning combinations. Okay? So you end up with a different kind of graph. And the strategy is a little bit different. You show the outputs within the circles instead of separately. Okay? There are multiple other steps involved. So I'm trying to give you a high level picture for now, and then we'll see the other steps in a second. But are you okay with it so far? Any confusion with it? Okay. I'm already marking it as a Moore machine, but you'll see why it is a Moore machine soon. So once you get this state graph, can you then convert it to a state table like we did for the first one today in this class? Did you see, hey, okay, we have 4 states now, S0, S1, S2, S3. I'm going to do it for like 1. Okay. What if I am at S0? What will be my next state? That will depend on the X input, right? If X is 0 while I'm at S0, should I stay within S0? So my next state will also be S0. But when I get 1 as an input, where should I go? I should go to the S1 state. So my next state is S1. Can you do it for the others? Notice you are using 4 states. That is the difference here. Okay. Finally, for the output, you don't necessarily, this is the other difference here. You don't need to look at what happens to x equals 0 or x equals 1. At every state, you have a unique output. That is the unique part of this approach. See, I just look at S0. What is the output for S0, folks? Look at this one. Yeah, so let me mark it again. S0 has 0, so 0. S1 has 0, 0. S2 has 0, fine. S3 has 1, fine. So I'm not going to look at what x equals 1 or 0 anymore, because our outputs for every state is already settled. Outputs will not depend on the x anymore. Are you good? This is deliberate. And just to achieve it, we had to create an additional state. For the first approach, we required less state. Yes, go ahead. Could you repeat that again? Sorry. For some reason, I'm not hearing you well. Sorry. How can you output what? No, the output for S0 is not 1. Output for S0 is 0, as you see. So basically, as long as you don't get the magic combination, your output is always 0, right? Output 1 represents you have gotten 1, 0, 1, right? When you are at S0, that means you are just getting zeros all the time. So your output is always 0. When you get to S1, your output is still 0. When you get to S2, your output is still 0. When you get to S3, that represents that you have traversed through 1, 0, 1. That's when your output is 1. Only that's when your output is 1. Does that make sense? Okay. Are you good so far? Everybody? Okay. And don't feel bad. I know, like, some of you will not tell me in class that, hey, I'm not getting it. I mean, I was one of those students, honestly, because I was a little bit shy. I never used to ask the professors in the class. It's just like my personality. So even if I didn't get something, I used to just, I know, like, keep it in myself and then struggle later on. But trust me, if you're struggling later on, you don't have to struggle alone. You can always come. I keep saying this over and over again. Some of you are using my office hours, some of you are not. Please come and talk to me. I'll be more than happy to go over this one-on-one. Okay, don't just take it as granted. Okay, I'm not gonna worry about it anymore, because you should. This is the foundation of digital design, by the way. So if your foundation is shaky, you can only imagine what happens to the rest of it, right? So that's exactly what I want to avoid. Make sure that you take help if you need it. Okay, next. So once you have this table, the next step is obvious. Remember, folks, I need to represent this 4 state with binary digits 0001 1011. So I'm going to do that exactly. Done. And once you decide S0 is 00, S1 is 01, and so on, you just replace these numbers in the table and you get the transition table. Is that new? Did you see it before? Okay. And by the way, present state is represented as AB, and the next state is represented as A plus B plus, like before. And our output is Z, like before. One thing that I want to point out that is deliberate in your textbook, notice 0001, not 10 here. It is 11 and 10. They deliberately chose it this way. Does it matter? Folks, does it matter? I can choose to represent S2 with 11. It is my choice. The reason why they chose to do it is because it is so easy to create a K-map. Because in a K-map, you need to do 0001, 1110, right? Otherwise, if I do 0001, 1011, and then represent the table, you have to be mindful when you're picking the numbers to the K-map. Does that make sense, folks? In case you ever get confused at home later on, instead of going in serial, they went in the serial that K-map prefers. That's all, without any loss of generality. Okay, so once you have this transition table, okay, so this is the last slide. Actually, I want to show you. You don't even have to go to the next one. Let me show you how to get to the K-map. So let me show you. My output Z, does it depend on X anymore, folks? Z doesn't depend on X anymore. It depends on what? AB. So I will have A here, B here, and I will have two combinations, 0, 1, 0, 1. Okay. So what is AB00? AB00 gives you Z equals 0. What is AB01? 01 gives you 0. What is AB11? 11 gives you 0. What is AB10? 10 gives you 1. Does that make sense? Can I populate the K-map this way? And can anybody help me get expression for Z? You just have 1, 1, right? What is not changing here, folks? A is not changing, so you have A. B is not changing, you have B, but B was 0, so you have B prime. Does that make sense? So your Z is now AB prime. Notice there is no X. So your output is only dependent on the flip-flop states, A and B. You are not directly using the input X to get your output. So your output is only dependent on the synchronized signals A and B. Okay, we are out of time. We finished the slide, but I know we had to rush through the last slide. So I will repeat it in the next class again. But I highly recommend and request you to try to think about it at home. Only then you know what you don't know. Okay, I will still repeat this slide in the next class and then move on to the next lecture. Okay, yes. Yes, yes, yes. So tomorrow. Thank you. Take care, everybody.